Welcome viewers. In this video we are going to do design of a transmission line tower foundation type 1 pad and chimney using Indian standard. This is part 1 out of 5. In this part we are going to discuss about the tower geometry, design foundation loads, soil parameters, foundation geometry which we are going to consider tentatively to check for all the parameters. And finally we are going to discuss about the analysis part. In that there are several cases. In that we are going to check the uplift resistance check in this part. So later videos we will be discussing more about other parameters such as bearing capacity, check for sliding, check for overturning, design of chimney, design of base slab. All those we will be looking in further parts of video. So let me go into detail about the Excel calculation which is prepared for demonstration purpose. On the screen you can see an Excel sheet which we are going to use to design the foundation type 1 pad and chimney for transmission tower. So here that first subtitle is tower geometry. In this we need to feed that input as tower leg slope tan phi and true length factor. Second subtitle is design foundation loads, which is multiplied with ultimate factor by 1.2. So these two subtitles are we already discussed in our last video about input for transmission line tower foundation. The link for the video is given in the descriptions. Third subtitle is subsoil parameters. So in this we are going to assume some value which is a relevant value. Generally this value we need to take from the soil report. So unit weight of dry soil is 1800 kg per meter cube. You can consider unit weight of wet soil is 900 kg per meter cube. Because of the presence in water, the density of the water will get reduced. Density of the soil will get reduced. Soil bearing capacity we can consider as 25,000 kg per square meter. Concrete weight is 2400 kg per meter cube. Grade of concrete M25, which is having a characteristic strength of concrete FCK as 25 megapascal, and grade of steel can be 415, which is having a characteristic strength of 415 megapascal. Next is foundation geometry. So that foundation calculation which we are going to do is a trial and error method, because we already having a lot of checks in future explanations. So in that, after coming that output, we need to change this dimension. If that output of the check for various cases, like for example uplift resistance, check for bearing capacity, sliding, overturning, design of chimney and base slab. In any of the case, if this dimension is not suitable, then we need to change this dimension. But for our initial stage, we can assume these dimensions. Start from this chimney size is 700 mm square chimney we can consider, which is projected above ground level of 300 mm. As in another video, we had looked into how to design of stub and cleat using American standard. So there is in that we got find out that the embedded length of the stub is 900 mm. So we can consider some extra of 200 or 500, which will come around 1500 mm, which is 1.5 meter. So we are considering here the foundation depth is 3 meter, which is more than the embedded length. And the next one is the drop thickness we can consider as 200 mm. The top of base slab, which is having a tapered size in order to optimizations, that thickness we can consider 250 mm. The vertical thickness of the base slab we can consider as 100 mm. The lean concrete thickness is 50 mm. Next is the drop width, we can consider 1.5 meter. The top of tapered base slab is 4 meter. The bottom of the base slab we can consider as 5 meter. And the excavation trench we can have 20 degree as a slope. Finally, we need to calculate the passive earth pressure coefficient, which is 1 plus sin phi divided by 1 minus sin phi. Applying this, we are getting 2.0397. Next, we need to calculate the active passive earth pressure, which is to be resist the foundation on sliding due to the external force. So for that, we need to multiply this passive earth pressure coefficient into the height and to the dry density of soil. So likewise, this height will vary according to the depth which is going down to the foundation. So we are just adding the total depth and multiplied with the passive earth pressure coefficient into the dry density of soil. So finally, in the base, we are getting 10,831 kg meter. So this is a pressure diagram of the foundation geometry by soil. So this is what the pressure diagram we had calculated. This we calculated only for the dry soil. Also we need to calculate for wet soil. In general, the wet soil is having the less density compared to the dry soil. So there will be a chance of sliding majorly only due to the wet soil because of the less density and less passive earth pressure. So what we need to do is we need to create the same kind of pressure diagram for wet soil also. So only thing, instead of considering the dry density, we need to consider the wet density of the soil, 900 kg per cubic meter. Remaining all the same for every depth. So with this, we are getting a less passive earth pressure to resist the sliding of the foundation compared to the dry soil. Dry soil it is 10,000. Here in wet soil it is 5,000. Next, we will be going to start the analysis part. In that, first we are going to check uplift resistance. So in that uplift resistance, we need to calculate volume of concrete. That volume of concrete is simple arithmetic calculations, like the base for compression and tension we need to calculate. For compression considerations, we can consider this lean concrete which is below the foundations, some 50 mm we had placed, that also we need to consider. So it is 5 into 5 into 0.05 is a volume of the lean concrete. Next one is the flat slab, 5 into 5 into 100 mm is the depth that we are considering. Next one is between the concrete volume of the flat and the tripod, that is below the drop. So the depth is 0.25, which is a tapered one. So the equation to find the volume of concrete for this portion alone is a square plus b square plus ab into h by 3. Here a is 5 and b is 4, h is 0.25 meter. Applying this, we are getting 5.084 meter cube. Next one is the drop volume, 1.5 by 1.5. The depth of the drop is 200 mm, 0.2 meter. So multiplying all these three, we are getting 0.45. Finally, the pedestal size, we know that 700 square meter mm. So that multiplying with the depth is up to the 2.4 plus above ground is 0.3. Total it is 2.7. So multiplying all this, and summation of total volume of concrete is 10.607. Next, we need to calculate the concrete mass. In that concrete mass, we need to consider two things, because this foundation we are designing for both the conditions, fully submerged and fully dry. For fully dry conditions, we need to apply for compression, and fully wet conditions, submerged conditions, we need to consider for uplift, because the tension force will be in the upward directions. Also, if the water is filled with the foundations, then the soil weight and concrete weight get reduced, so that it is challenging for uplift force. So we need to consider both the case. So first one, for compression, we can consider the dry weight of concrete and soil. So for that pedestal size, we know that 700 mm square. So that we are multiplying. When if it is above the soil, we need to consider only the dry weight of concrete. So here you can see 0.7 into 0.7 is the size of the pedestal, and 0.3 is the height above ground. That multiplied with the 2400 is nothing but it is a density of concrete, dry density of concrete. Here you can see as a subsoil parameters. So it is 343. So the same is applicable for uplift condition also, that is in wet fully submerged soil conditions, because the above ground level there won't be any submerged considerations for soil, only the concrete weight we need to consider. Next one is below ground level conditions. So in this, the total volume we had calculated is 10.607 dry volume, that minus this pedestal sizes which is above the ground will have one quantity in cubic meter, that should be multiplied with the relative weight of concrete, that is below soil we need to deduct the soil weight also in concrete density. So because we are going to calculate separately the soil volume and its weight, so here 2400 is the dry density of concrete and 1800 is the dry density of soil, that should be deducted with the concrete weight and multiplied with the concrete volume, net volume. So we are getting 6276. So these are the total volume we need to total mass of concrete we need to consider for compression case. And coming to the uplift case, for wet soil we need to consider. So above ground we can consider as a same in compression case, and for below ground we need to consider the soil weight also, submerged weight. So submerged weight is nothing but the concrete mass density we know is 2400. In that we are going to deduct 1000 kg per meter cube, which is a water density. As there is a subsoil, also we need to deduct the wet soil density 900 kg. So that we are multiplying with the concrete pedestal or chimney size. 0.7 into 0.7 into 2.4 is nothing but the clear distance between the drop and the below ground level pedestal height. Next one is the weight of concrete below the pedestal. For that, the total concrete volume we are deducting the pedestal volume alone. So 10.607 minus 1.323 is a chimney below ground level to the top of drop, and 1.25 is the lean concrete. So the lean concrete also we need to deduct in case of uplift case, because that uplift, the lean concrete will be act like a separate element, it won't connect with the concrete foundations. So that we are deducting here. And finally the same way that wet density of concrete, that is 2400 minus 1000, that also should be deducted by the wet soil density. we are getting 4017. So in total it is 4958. Next we need to find out the soil volume. Soil volume calculations, we need to have this sketch in the right hand side. That is the green color indicated the foundation size. It is a rectangular. So it is 5 by 5. That is inside we are calculating. So the soil volume is 5 by 5 into 2.4 plus 0.2 plus 0.25 is nothing but the summation of the clear distance of pedestal below or chimney below the ground level plus depth of drop plus depth of sloped footing. So multiplying this, we are getting the volume of inner size, that is base slab size. And the next one is we are having a 4-side orange color strip, which is because of the slope which we are making here, 20 degree. So this width we need to consider. So that width we can calculate by tan 20 into 2.85. 2.85 is the depth up to here. So 4 times 5 point, sorry 5, 4 times 5 into, this looks like triangle, so we need to consider half of the width. So that half 1 divided by 2 1 divided by 2 into 4 will comes as 2. So 2 into 5 plus the depth we need to multiply it one time, and again the depth should be multiplied with the tan 20 like to find this width. It is nothing but the half of BH equations. The B is at tan 20 2.85 and H is at 2.85. So that is why this H, that is 2.4 plus 0.2 plus 0.25 is multiplied 2 times, that is squared into tan 20. Tan 20 is to calculate this width. Half we need to consider for a triangle, so half into tan 20 into H square into 4 times this strip width, because this triangle is going to form in the 4 sides. So that is why 4 into 5 into half should be multiplied with the 4, then it will comes into 2 into 5 into height square into tan 20 will give 29.56. Then we need to consider this small strip, this part alone. So it will act like a circular part because of the corner edges. So we need to consider by into, as from the base if we are calculating we need to consider 1/3 of the triangle shape. So it is like tan square, because this side tan 20 into height and another one side also we need to consider the tan 20. So it will like tan 20 square into height square, because this width in order to arrive, as we know that we need to consider the tan 20 into height. So that tan 20 into height will be a square shape, square 2 times we need to consider. So that's why tan 20 square into h square into the depth is h. So this 2.4 plus 0.2 plus 0.25 is nothing but h, we can call it as. So it should be h cube, as it is both side a triangle strip we need to consider 1/3. Also the by d by value is 3.141 into 1.3 tan square h cube. So this is the volume. So total soil volume, we are going to summation this 3. Then wet mass is nothing but volume into wet soil unit weight. Similar like for dry mass, volume into dry density. And finally the total resistance against uplift. So for that we need to add the weight of concrete and weight of subsoil. So for uplift we can consider only the wet density of both the concrete and soil. So these are the calculations which we done earlier. And we are going to just multiplying the actual actual uplift during normal tension and broken wire conditions to find the factor of safety, which should be greater than 1, then we can call it as safe. Similar like for broken wire conditions, we are considering the actual force 14,180. That should be divided by the summation of concrete and soil mass, which is greater than 1, hence safe. So why we are considering the factor of safety? One is we are considering the ultimate load cases, which is multiplied alright by factor 1.2. So it is better for economic conditions, we can consider here as a 1. So this is all about the check for uplift. We will meet in another video for more detail. Thank you. Look description for more related videos. Subscribe to this channel for more updates.